some question of linear operator which had come in competitive exam. Today, at first I will see one question which had come N.B.H.M 2020 exam as a nilpotent operator and Jordan canonical form. Then I will discuss some nice property of nilpotent operator. This is our second goal of this lecture. And next goal, I will discuss the new operator, idempotent operator. Question is, consider T be a nilpotent operator on a vector space R5. We all of us know nilpotent means T to the power n equal to 0 for large n. And consider Di denote the dimension of kernel of Ti. Then, which of the following can possibility occur as a value of d1, d2, d3? Write yes in the box if it can and no if it cannot. Here notice d1, d2 and d3 denoted the possible dimension of kernel of t to the power I. Okay? We all of us know. Since here T be nilpotent operator on a vector space R5, so obviously t to the power 5 equal to 0. And we all of us know in nilpotent operator the number of basis Jordan block is equal to the nullity of T. We all of us know this is. And since Di denote the dimension of kernel of Ti, then d1 always imply dimension of null space T, d2 imply dimension of null space T square, and d3 imply dimension of null space Tq. And since dimension of null space means Tv equal to 0, and from this expression we can tell T square V equal to 0 and T cube V equal to also 0. It means null space of linear transformation contain null space of linear transformation T square and T square contain null space of linear transformation T cube. That means dimension of nullity is denoted as d1, d1 less than equal to d2 and d2 would be less than equal to d3. This is the relation. Okay? And here we have to find the possibility of d1, d2, d3. At first consider, if we consider d1 equal to 1, d2 equal to 2 and d3 equal to 3, we all of us know dimension of null space means number of Jordan block, which is actually, since in nilpotent matrix only eigenvalue is 0, this is equal to geometric multiplicity of 0. So, since here t to the power 5 equal to 0, that means here 5 cross 5 matrix with one block, and notice for nilpotent matrix one block would be such type, and here rank of the matrix is 1 1 1 1, that means rank of A is 4, and rank of A square, if you calculate, then always it would be reduces, it would be A times A, it would be reduces one element. So rank of A square would be 3. Then nullity of A square would be 5 minus 3 equal to 2, and rank of A cube would be, since here A cube, so it would be reduces to 1. Just calculate. So rank of A cube would be 2 and nullity of A cube would be 5 minus 2, which is equal to 3. So notice nullity of A square equal to 2 means there exists 2 blocks of the linear transformation A square, and nullity of A cube equal to 3 means there exists 3 blocks of the transformation A cube. Are you getting? Notice, from this observation, it is true D1 contain D2, D2 contain D3. Are you getting the geometry? This is very nice geometry. Okay? Oh well. Option 1 is the right option. Now consider option 2. Here D1 equal to 2. Now we have to see, is D2 and equal to 3 and D3 equal to 5? For this, D2 equal to 2 means here 2 block exist, and in 5 cross 5 matrix 2 block would be such type. Here 1 block and here another block. And here rank of T would be for this block 1, 2, 3. And rank of T square would be for this block 1 would be reduces. That means this is equal to 1. And for this block 1 also would be reduces. That means since here for this block rank is only 1, that means this would be 0. Therefore, null T square would be 4. 5 minus 1 equal to 4. And rank of T cube would be for this block 2 would be reduces. That means this would be 0. Also, here also would be 0. That means rank of T cube would be 0. That means null T cube would be 5. Now let's see the option. I will consider D1 equal to 2. Then here 2, 3, 5. This is wrong option. And here 2, 2, 4. This is also wrong option. Only fourth option is a right option. 2, 4, 5. Okay? Oh, see our second goal. Some nice property of nilpotent matrix. First question. Consider A and B are two nilpotent matrix. Then, is there some B nilpotent matrix? Also, if A and B are two nilpotent matrix, then is their product B nilpotent matrix? Let's see this expression at first by an example. Consider two matrix A and B. Notice here AB is strictly upper triangular and BB is strictly lower triangular. Means obviously A and B are nilpotent matrix. Now I will say they are some B not nilpotent matrix because A plus B would be 0, 0, 2, 0, 2, 2. This is not B nilpotent matrix. So, if A and B both nilpotent matrix, then their sum may or may not be nilpotent matrix. Are you getting? So, their product may or may not be nilpotent matrix. Okay? Similarly, for product, at first consider these two nilpotent matrix. Similar to before, this is also nilpotent matrix. And their product would be 0, 0. So, obviously, this is nilpotent matrix because null matrix always be nilpotent matrix. But this not always true. Because consider these two matrices. Obviously, both A and B are nilpotent. But their product is this matrix. Here, AB not be nilpotent. Okay? Are you getting? Oh well. Then my question, when two operator be nilpotent, then when their sum always be nilpotent and when their product always be nilpotent? This is possible when these two operators be commute. That means, suppose T1 and T2 be two nilpotent operators that commute each other. That means T1 T2 equal to T2 T1. Then their sum and their product are always be nilpotent. For this, consider a linear transformation T1 from vector space to vector space such that T1 to the power k equal to 0 operator. Also consider a vector linear operator T2 from vector space to vector space such that T2 to the power k equal to 0 operator. And the mapping is such type: T1 map from vector space to itself and T2 map from vector space to itself. Now we have to prove their product always be nilpotent, and this is possible when they are commute. That means here their product T1 T2 from vector space to vector itself, and since they are both commute, so this is equal to, we can write T2 T1 from vector space to itself, and T1 T2 to the power k equal to, actually we can write T1 T2 times T1 T2 up to T1 T2 k1 times, sorry, k times, and since T1 T2 equal to T2 T1, that means we can interchange this as, this is T1 T2, this is T2 T1. Similarly, we can interchange this. We can bring all T2 on the right hand side. Also we can bring all T1 in one side. Then this would be T2 to the power k times T1 to the power k. And since T1 to the power k equal to 0 operator and T2 to the power k equal to 0 operator, that means this is equal to 0 times 0 equal to 0. Therefore, T1 T2 to the power k equal to 0 operator when both T1 and T2 are commute. Okay? Are you getting? Oh, well. We can prove their sum also be nilpotent when they are commute. That means when these two products be commute, then their sum and their product always will be nilpotent. Okay? Oh, well. Now I will discuss our next goal, idempotent matrix and idempotent operator. Idempotent operator is nice linear transformation. This is actually the projection. We all of us know what is the projection linear transformation. This is the picture of projection map. Consider P be a linear transformation from Fn to Fm. We say that P is projection if P compose P equal to P, and consider A be any standard matrix of P. Then P compose P transform A square equal to A, and if A square equal to A, then the matrix A is called idempotent matrix. Are you getting what is the idempotent matrix? Very important property. When A square equal to A, then this matrix is called idempotent matrix. And this matrix always would be symmetric matrix. Are you getting? Oh, well. And in my next video, I will discuss the property of idempotent matrix elaborately. Today I will stop here. Okay? But at first I will highly recommend you, please see today's video with pay attention. Then our next video will be so easy. Thank you so much.